I was saying last Tuesday we did this theorem that sort of felt like really heavy on notation, but actually is quite simple and it's very important. So let me just, or I should say a certain implication of it will be very important. And this theorem was the following. So if f is analytic at z0 and f of z0 is w0, then and say, right, so and so this means in particular that right, f of z minus w0 has a 0 at z0, right? Because otherwise that equation would have been true. Say has a 0. So we just want its order as a 0 at z0 of order n. Okay. Then we show that if epsilon bigger than 0 was small enough, then for that epsilon there existed a delta, right, bigger than 0, such that for all so for all a in the image, right, for all a such that a minus w0 is smaller than delta, and let's say bigger than 0 because I might want to say a bit more. That part is not really that important. Then basically I'm saying that if I pick epsilon small enough, and then for that epsilon there exists a delta in the image such that if a is close enough to w0, then the equation, right, the equation fz equals a has exactly n solutions, exactly n roots, and solutions, or I mean, different people call this solutions or roots depending on the language in right that disk around epsilon around z0. So in z minus z0 smaller than epsilon. Okay, so this sounds like a lot of notation, but all this is saying is if I have a 0, right, if I have a solution to an equation, we can think of just w0 as 0 just to be simpler, right? If I have a 0 of order n, then if my target point rather than w0 is something very, very similar, then I'll still have n solutions to that equation. And maybe a point that one should make is that, right, that we essentially prove this by making use of the fact that we could count number of solutions of equations by just integrating essentially f prime over f around the curve, and we could count the number of solutions inside. And if basically we saw that if we wiggled w0 a little, that count couldn't have changed, right? There was the proof technique. Now, maybe worth saying is if n equals 1, so what do I mean by this? If the 0 is of order 1, or in other words, right, if the derivative at z0 is not 0, right, then actually this means that there's only one solution, right? This means that there's exactly one solution. And so because there's exactly one solution, we actually get that the map, right, f is 1 to 1. Right? In particular, it's right. So f is 1 to 1. You should view it as going from a certain open set of the disk, right? Going from a certain open set of this disk, wherever the set of solutions is, to the disk at the image, right? So this disk here, right? And in particular, it's not so hard to see. I mean, this is again something that maybe it's best to just sit down and try to see it yourself. That actually, f of course is continuous. F has an inverse, right? Has an inverse that is continuous. Okay, maybe this will be more obvious in a second, right? But f has an inverse that's continuous, right? Where I think of f as going from some open set u inside this disk, right? So inside this z such that z minus z0 is smaller than epsilon, right? The set of solutions going to that disk that I just described, right? So right, so going to the set of A such that okay, but I mean, it doesn't really matter what these sets look like, just means that, f is actually around this point is a one-to-one map, and actually the inverse is continuous, and so right, this is what we call f is actually a topological map. So f maps, right? F in this case maps topologically, just means that it's continuous and its inverse is continuous topologically. A neighborhood of Z0 to a neighborhood of W0. Okay, this will be more clear in a second, right? And also, it's not so hard to see, right, that by say the inverse function theorem or something, that actually f prime f is also analytic. So f inverse, the inverse of f is also analytic in this neighborhood, right? The inverse of f is also analytic. Right? Of course, this only happens because, right? Because the derivative, if the derivative is not zero, this is exactly what is needed for there to be just one solution, right? So meaning that once I'm in the image, once I'm in this place in the image, I have just one, right? The inverse is well defined because this is just the zero. Yes, someone put it out in the chat. Of course, this is zero, not one. Sorry. Yeah, this is different than zero, right? Because I want the zero to be of order one. Yeah, so F is an homeomorphism. Yes, this is just the same word for topologically. Yes, F is a homeomorphism is just the same word, right? So F is an homeomorphism. Yeah, depending on the on the community, these things are called different things, but it's all the same, right? It's just a map, one-to-one map that the F is continuous and F inverse is continuous. Okay, and then the fact that it's analytic just comes from the fact that the derivative is non-zero, that the inverse is analytic. But what I want you to take away from this is that it's mapping, right? It's mapping, F is mapping in a way, if n is equal to 1, such that, right, every point around the image, in a little open set around the image, is one and exactly one point in the neighborhood of Z that maps to it. Right? And so that's where this correspondence is coming from. And in particular, an immediate corollary that comes from this, and maybe this is even the easiest way of seeing that the map is topological, right? Well, like one obvious way that one obvious theorem that comes from this, so corollary, right? So okay, maybe just to not be confusing, let me say now, right? So in order for the map to be topological and for the inverse to be well defined and all of this, we needed that n equals 1, right? Because if it's a zero of order 2, then basically there'll be some kind of branching, and this can actually be explicitly understood. Right? So if I have, say, the zero of order 2, then basically every single point in the neighborhood of W0 in the image will have exactly 2 solutions. And so there's some branching going on. Is exactly what happens with, polynomials and when the issues that show up when you take square roots and things like this. Okay, but now what I'm going to say, n doesn't need to be 1. So let's go back to n is no longer required to be 1. To be equal to 1. Okay, so now I'm allowing, any analytic function because I want to have, theorems that hold for any analytic function. Okay, so I claim one of the most important corollaries of this. So corollary of this is that if f is a non-constant analytic function, then f maps open sets to open sets. Right? So remember, continuous functions don't need to map open sets to open sets. Right? In particular, continuous functions by themselves, they do not need to map open sets to open sets, right? Just think of, this is not obvious for continuous functions. Just think of, say, f of x equals sine of x, right? F of x equals sine of x clearly, doesn't map open sets into open sets. If I map, say, the set, minus 100 to 100, this set gets mapped to a closed set minus 1 to 1. Right? It goes open to close, right? The definition of continuous was sort of, I wouldn't say the opposite, but it was that the inverse image of open sets needed to be open sets. And what we're saying here is that, because analytic functions are so nice and such magical objects that they need to map open sets to open sets. Right, and this is sort of obvious now, right? Because the proof of this follows, right? So proof of this follows almost immediately, right? So just take right? You can just take for any open set, say U, right? So take for any, any U open set in the image, open set, right? And now take, right? Take Z0 in U. Okay, and now look at F of Z0, right? Okay, so, or let me say open set, okay? And now look at, take some point W0 in the image of U, right? We want to prove that there's a neighborhood of W0 that's still contained in the image of F of U, right? But now, if we have W0 and F of U, this means that there exists, right? There exists some Z0 in the open set U, such that, right, F of Z0 is equal to W0, right? And then we can just use use the theorem above, right? The theorem above says that there exists delta, right? I just pick epsilon small enough. There exists delta bigger than 0 such that for all W in the, near W0, so W minus W0 smaller than delta, there must exist Z, right, in the neighborhood of Z0, but we can pick the neighborhood small enough so that it's inside the set, so there exists some Z particular inside the set, such that, right, F of, F of Z is equal to W, and so W is inside the image of F of U, and so, right, this means that, the set, this implies that, wait, stop working, sorry. So this implies that, the points, the set of W such that W minus W0 smaller than delta is contained in F of U, and so it's open. Okay? And so this implies that, this is basically the proof of the theorem, right? It comes almost straight away from the thing we had before, right? So this ends the argument. Okay, so these analytic maps are definitely like special. I mean, we've seen, gazillions of examples of reasons for analytic maps to be special. This is just yet another one, but it tells you that they're very good also at keeping topological properties, right? If I want to study some object, right? Some topological object, some manifold, some differential manifold, whatever, then if I apply to it an analytic function, I keep a lot of its properties, right? Because the fact that the map is continuous and the inverse is continuous, the fact that it's homeomorphism allows me to keep a lot of properties, and this is crucial in many areas of geometry and topology and so on. But sort of from the analytic viewpoint and from the viewpoint of understanding analytic functions and estimates, and also shows up a lot in differential equations, we get a very important analytic implication of this. I mean, and this one is sort of extremely, Larry, is extremely useful, right, in exercises and whenever we want to prove something, and it sort of is an ingredient to often really beautiful proofs, which is known as the maximum principle. This is one of the nicest, this is really one of the nicest ingredients of many, solutions to either proving theorems or exercises or something. So the maximum principle says that if F, right, is analytic in an open set, or let's say in a region, analytic in an open set, omega. Okay, I mean, I can talk about, let's say, open set omega. Okay, it doesn't need to be connected for this, but okay, it's not really that important now. Then is an open set, then it has no maximum. Then f of z does not attain the maximum. Sorry. In omega. Okay, so take a second to sort of absorb this, because this is really, again, this is, I think, if you like the first time you think about this, it's kind of surprising, right? Maybe I should say in a region, because we've been always talking about regions. There's no need. So let's say in a region. Okay, to not create, be, okay. Right, so an open connected set. Ah, yes. Someone asked f constant. Yes, of course, f cannot be constant. N non-constant. Yeah. The boring functions don't count. Of course, if the theorem above only applies for non-constant functions. Is that right, Ted? Yeah, a non-constant analytic function. Okay, so a non-constant function. Yeah, so someone asked if I'm talking about global maxima. Okay, very good question. So let's think about this a little bit together. So okay, so the theorem is for a region f an f non-constant, then the absolute value of f does not attain a maximum in omega. Okay, so here I mean a global maximum. I mean that there is no point in omega that is bigger, right? What I mean by this, I mean, okay, let's interpret this. I mean that there's an exist z in omega such that f of maybe I should call it z0, such that f of z0 is bigger or equal than f of z in absolute value for all z in omega. Right, that's what I mean. Right, there's no point that sort of rules over all the other ones. Okay? Now, someone in chat is asking if okay, what like right or I mean, I guess they're not explicitly asking this, but I imagine this is the follow-up question that okay, what about local maxima, right? Like it could be that you're not you don't rule all of omega, but you rule at least the ones around you. But you also cannot rule the ones around you, right? Because otherwise I could just do my theorem for a little neighborhood around the point, right? So if you imagine, let's say that I plot the absolute value of f, and I would get, let's say that I plot, think of this as C, okay, have some, imagination, and this says the absolute value of f, right? If I'm something like this, okay, let's say that I have a little mountain here, right? I also can't have this kind of picture, right? Because even though it's not really a maximum because, this guy over here is bigger maybe, but if I look at this point, right? So if I go and see this point, if I look at a neighborhood around it, if it's a local maximum, it would be a maximum on this neighborhood. So now I would just apply the maximum principle to that set, right? So they can't be either local maxima, right? They're also not allowed. Okay. So this is, this might not seem, and again, the example, you can keep in mind the example of the sign, right? Like clearly, it's a special thing about analytic functions. And in particular, it implies already tons and tons of things, right? So someone is asking what would be the problem with this function. I don't know if you mean this function or the sign. So for the sign, the problem is that the sign over the complex numbers does not have that same behavior, right? It looks like an exponential when viewed in the imaginary part. And for this picture, yeah, this function can't be analytic. And so basically, when you have a point, there needs to sort of be a direction in which it grows. Yeah. Yeah. So Liuville theorem. Okay. Great. I'm happy I'm getting so many nice questions. So someone brought up Liuville theorem, right? So Liuville theorem was a statement for the whole plane. That if the function was bounded in the whole plane, then in the whole complex plane, then it needs to be constant. That's different, right? I mean, I don't know. Yeah, I don't think you can just get it straight from this because, right? It could be that the function just keeps growing, but just really, really slowly, right? You could imagine a function, right? Okay, so addressing the issue with the comment with Liuville's theorem, I don't know. It could imagine a function that goes something like maybe outside for large, for large z, say, for a large modulo of z, it goes like f of z equals, say, a minus 1 over z, or something like this. Right? Let's not worry about what happens near 0, but what happens very far away. And very far away, this function is bounded, but it doesn't have a maximum, right? If I go further and further away, I get a little bit bigger, just not a lot. And so Liuville theorem prevents these kinds of things from like tells you that no such thing can exist, while the maximum principle doesn't say anything about it. I think, yeah. Does this make sense? Does this answer the question? Okay. All right, great. Thanks for the great questions. Yeah. Okay. So now, this implies in particular, that if I have, okay, so let's now collect implications of these statements. So another corollary. Okay, if f, so if f is continuous, let's say continuous in a closed bounded set E, then if f is continuous in a closed bounded set E, then and I need more. I need analytic, of course, and analytic in the interior. Analytic in the interior of E, then the maximum of f is attained in the boundary, right? In the boundary of E. And this is again a very powerful theorem, right? That if I have a function that's continuous in a closed bounded set, then actually and analytic in the interior, then the maximum needs to be attained in the boundary. Right? I mean, and this is now very easy to prove, right? Because if the set is closed and bounded, it needs to attain a maximum. We know that from topology. I mean, we even saw this when I gave like a week on topology. And because it cannot attain a maximum in the interior, well, there's only one place it can attain the maximum. It needs to be on the boundary. There's no other option. Okay? Now let me give you sort of before showing another theorem, let me try to give you some intuition, which is that things like this are true sometimes for like functions that are solutions of differential equations, right? So let's imagine, okay, so a little side note, right? Let's imagine that I have, some kind of problem where a physical problem in which I have some kind of region and I have some heat element, right? Whatever, fixed temperature here, fixed temperature, right? Around, all the way around there's fixed temperature. And now I ask for what is the temperature inside, right? This is a typical question in differential equations, in physics, and so on, right? And so this is a solution to some differential equation, some diffusion differential equation, and you could ask, what is the solution of this? You certainly expect physically that the maximum and the minimum of the temperature should be attained on the boundary, right? So why would if you think of a physical system where you have some kind of heat elements and fixed temperature around outside, right? Why would it ever be hotter in the middle or colder in the middle than the minimum or maximum side of the outside this, right? So there are theorems of this type for many solutions of differential equations. You can think for heat and say diffusion equations. This is very easy to see, and it probably is that if you've taken a course on these things, you might even have seen these theorems. And now you might have already be seeing the connection as well, which is that, right, we show that analytic functions have this really nice, right, they need to be harmonic, and the real and imaginary part need to be harmonic conjugates and all this stuff. And right, this is essentially the same thing, because equilibrium points of these diffusion equations, they're also harmonic functions. So you can view this maximum principle as coming from the property of harmonic functions, and this sort of ties together all this stuff that we saw, and I might talk a little bit more about it. But just for those of you that have studied differential equations, I just wanted to, it's very useful to have a picture like this in mind. Okay, I saw there was some activity on the chat. it seems maybe did it get solved or? I think so. Okay. If not, please ask again. But thanks for all the questions and answers. Okay. So um, okay. So let me before we go further, let me just say that there's actually another easy proof of the maximum principle, right? So there is an analytic proof of the maximum principle, right? So there is an analytic proof of the maximum principle. It's worth mentioning, right? Which is just through like almost everything we've proved so far in this class comes from the Cauchy integral formula, right? So if I take from Cauchy integral formula, right? We gave sort of a topological proof, but it's the same. It's the same. Actually, did I? I might not ever. I now don't remember if I didn't say anything about the proof. Maybe I should just write a word. Okay, because it comes as a corollary, but maybe I should describe how it comes as a corollary. So let me take a side note to might not be completely obvious. So let me maybe prove this a bit more, not just say that it's a corollary, but say how it is a corollary, right? So if f is analytic in a region, right, then suppose, right, take let's go by contradiction, for example. I mean, there's many ways of proving this, but say maximum is attained at z0, right? Then and let's say f of z0 is equal to w0, right? We know that take a little ball, right? A little ball around z0 with say radius epsilon, right? Such that it's still analytic there, right? Still in the region. We know that f, right? So f of this ball is open, and f of this ball contains w0, right? So it must contain points with a larger absolute value, right? Because, right, and so this is the proof, right? And so this would be a contradiction, because then it wouldn't be a maximum, right? And another way of saying this is must contain like some ball. There must be some ball around w0 with radius delta that is contained in f of b, but this ball, right? This ball for sure contains points with bigger norm than w0, right? I mean, proof by picture. If I take the complex numbers here and I have w0, if I take any ball around it, there'll be some other point that has bigger norm. Okay, so this is the proof. Sorry if I didn't make it clear enough earlier. But so let me give, right, so it follows immediately from topological properties of the map F, but actually one can give an analytic proof, right? So the analytic proof is also quite nice, which is just take, I'm just going to show that z0 is not a maximum, right? You can think of it this way, or you can think of it as contradiction. But take, okay, let me get the right pen. So let z0 in omega, right? And take a circle, take, an epsilon, let's say an epsilon bigger than 0, such that the ball of z0 around the closure of the ball, let's say I want the boundary also, right? I just take epsilon small enough such that the closure of the ball is inside omega. Okay, then I have Cauchy integral formula, right? So from Cauchy integral formula, I get the following. I get that f of z0, right, is equal the integral around the curve, which is still inside omega. So I take I take I take the curve around the ball, so z0 epsilon, right, of f of xi over xi minus z0 dxi. Okay, and so now we can parameterize this curve. This is very easy. Oh, 1 over 2 pi. I always forget the 1 over 2 pi I. 1 over 2 pi I. Okay, so what is this equal to? 1 over 2 pi I. I'm just going to do the parameterization. 0 to 2 pi. Okay, so I get f of z0 plus r e to the I theta. I'm just going to do the parameterization, right? This is now the parameterization of the circle. Nothing more to it, right? This is my c, right? So I have my change of variables, and okay. And so what do I get here? C is z0 plus r e to the I theta minus z0. So far, so good. Then I have dc over d theta and d theta, right? Okay, equal to. And now I have, okay, equals. Let's continue the calculation. 1 over 2 pi I. Okay, I mean, of course, this is all going to cancel out. We've seen a calculation like this before, but it's always a good one to do. Okay, so the z0 cancels, so I get r to the ei theta. And now the derivative of that is what? It's r times, right, I from the derivative, from taking the derivative of ei theta, I get an I, and then I get again ei theta. Okay, d theta. And now there's a bunch of stuff that cancels, right? This r cancels with this r, this I cancels with this I, and this e cancels with that e. Great. So now I have 1 over 2 pi, 0 to pi, and I'm sure you're seeing already what's going on. The radius is epsilon, not r, sorry. Okay, I'm just so used to write radius. Okay, epsilon equals to r, sorry. I'm just so used to writing the radius being r that I, okay, and so now d theta, right? So what we get here, we get that immediately f of z0 is smaller or equal by just triangle inequality 1 over 2 pi, right? This is now an integral over the reals, 0 to pi integral of f z0 plus r e to the I theta absolute value d theta. Okay, and now just looking at this formula, we get everything we could possibly need, right? Because let's just interpret this, right? If, you know, if fz0 was maximum, right, was a maximum, right, then this, right, because if you think you're integrating something over 2 pi I, over an arc length of 2 pi, right, divided by 2 pi, so you're basically averaging the absolute value of these things, then basically f of z0 plus r e I theta would have to be exactly equal because it cannot be bigger, right? Right, it cannot be bigger, and so, right, because fz0 is bigger, is the maximum, then here it can never be bigger, so this needs to be equal to f of z0, right, for all, in the whole circle, right, in the whole circle. Moreover, for any, in any small enough circle, right, because I can always take epsilon smaller and everything works. And so this means that if it's a maximum, then actually f of z, sorry, the absolute value needs to be constant, right? So needs to be constant in a neighborhood of z0, right? Because otherwise, the right, you have for any circle, it needs to be the average of the things around it. If I have z0, right, and I'm averaging the value of the absolute value around, because z0 is the maximum and is also the average of what's around needs to be equal in everything. And then it's not so hard to see. I mean, there's a few different ways of seeing it. It's not so hard to see that this implies that f of z actually is constant itself. Is constant. Right? I mean, you can do this in a variety of ways. with a lot of the stuff, the identity principle type ideas that we've done, one can prove this. So, okay, oh, I see there was a lot of activity in the chat. Let me see. Okay, let me go see what, if anything is unclear. Okay, so okay, so maybe in case this is not obvious, let me reiterate. So I've done basically two different proofs of the maximum principle at this point. Okay? So one proof, okay, so let's take a step back maybe. Let me zoom out a little. So, okay, so we've done, right? There was that theorem that we had. That theorem that we had implied that f needs to non-constant analytic functions map open sets to open sets, right? So this we showed. Okay? Now, from this, a corollary that came, right? A corollary maximum principle, a corollary of this this fact, right? The corollary of this fact, right? The maximum principle was immediately a corollary of that, and the proof is here in green, right? Because it maps open sets to open sets. Okay? If you look at, if you had a maximum, you look at an open ball around that maximum. It needs to go to an open set. But this means that if z0 is the maximum, then w0, the image of f0, needs to be the point with the biggest absolute value. But if a neighborhood of z0 goes to a neighborhood of w0, if you have a point over the complex plane, any neighborhood of it will contain points with bigger absolute value, right? Just take, think about, you have complex plane and take a point w0, take any neighborhood of it. There'll always be a point in this direction, right? There'll always be a w0 times 1 plus some tiny, tiny delta, which has bigger absolute value. And so for sure, this can't happen, right? So just because the function maps open sets to open sets, this could not possibly happen. In fact, if you think about it, you immediately get maximum principles, not just for the absolute value, but for the real part, for the imaginary part, and for a bunch of other stuff that you might think of. As long as the thing you're trying to maximize satisfies this property that for any point, if I have an open set around it, there's always someone that beats me, then you're going to get a proof immediately for that, right? So if instead of absolute value, I take real part, imaginary part, I mean, whatever, these things are still true, right? Because, for any open neighborhood around W0, I always have a point with bigger real part, with bigger imaginary part, and so the theorem would apply nonetheless. Now, what I was doing now was a second proof of the maximum principle, right? Just to show you an analytic proof. Basically, what we just did was a topological proof, right? From topological properties of the mapping, we derived the analytic principle. Now I was going to give you an analytic proof. What it means by an analytic proof is one in which I have to do calculations, right? Rather than one in which is sort of just what's called a soft argument, right? In which you don't actually need to do any calculations, right? So here I needed to do calculations. And the idea was to use Cauchy integral formula, that's the calculation I did, to show that the absolute value around a point, okay, like here, let me maybe zoom in a bit more again, right? The absolute value around a point here, z0, is smaller or equal than the average of the absolute values on a circle around it. And so if you were the biggest one, right? If z0 were the biggest one, how can it possibly be an average of the absolute values of the points around it? There's two things that might happen. Either the absolute value of all the things around are not all the same, and then for sure you need to be smaller than the biggest one outside, and so you could have not been a maximum to start with, or the absolute value of everything is the same. And so the only possibility, if z0 is a maximum, if you do this analytic proof, is that actually this, like the norm of fz needs to be constant in any neighborhood of z0. Okay? And then it's not so hard to see that fz needs to be constant. Okay, I think you can even get this probably from Cauchy-Riemann, but you can certainly get from the ideas that we did for identity, theorem, and so on. And again, you can, it's easy to do this for other properties, not just necessarily the absolute value, right? If I take the real part or imaginary part, nothing really changes here, and I get the exact same argument, and then it's even maybe easier to see from Cauchy-Riemann. Okay, so we just did two proofs, like two different proofs, two different. Sorry if it wasn't obvious that this is what I was doing, two different proofs of the maximum principle. Okay, so now I have 2 minutes. So let me just say something, which is that sometimes you can get better, right? So just because you know that the function has no maximum. So if I give you that the function has, if I tell you that the function in a certain disk is smaller or equal than something at the boundary, right? You know that inside it needs to be smaller or equal, but maybe you can do more. And so an example of how you can get more, you can get sort of better estimates in some cases, better estimates, is through you can do some better analysis. And one example is known as the lemma of Schwarz, so a Schwarz lemma. And this is a very good example of how you can get a better estimate. And so this is actually in the homework. Right, so the idea is to use the maximum principle to get a better estimate of this. So just before we finish, let me just say basically what we're going to do starting next week is the general Cauchy theorem. Right, so we're going to try to answer the question for which regions and or curves or closed curves omega is Cauchy's theorem true. Right, so when is it that we have this? So this is what we're going to do on Tuesday. Okay, and so this will basically involve a lot of topology and something the notion of simply connected. So we'll focus on C, right? So we'll focus on what happens over the complex number. So we won't talk much about topology, and I guess in some sense algebraic topology over for higher dimensions, but I'll briefly mention it